Hello guys, welcome to the final session with lots of information about my rewinding project. Rewinding a Revolt RV-160Em. Warning, that video will contain lots of information and data. I will talk a lot, so if you're not that much into electrical engineering or motor technologies, just skip that video and enjoy another wonderful video proposed by the YouTube algorithm. All right, so let's start with the original motor. You can see it over here. It has, how does that work? Like that. It has 9 turns. And according to their webpage, which has lots of information, lots of data, it should run with 32 kV. When I measured the no-load speed and backwards calculated the kV, I ended up with 30 kV, and that was the initial point where I said, no, that's a little bit, that's not enough in my application. I need a little higher kV. So I wanted to have a machine with just 8 turns, and instead of buying a new one, I started the conversation with Revolt and said that I probably need to disassemble their original winding package, destroying the state, and they said, hold it, before destroying something you will get empty iron package and bushings and so on and all the information. So that's where it started over here. If I talk about resistances, inductances and so on, I always refer to 2 outer terminals and the third one is left open. That means internally it looks like that. We've got then the 3 winding packages, which are connected as delta internally. That's what it looks like. Talking about 2 outer terminals, third one is left open, and internally the delta looks like that. 2 are connected in series and 1 is connected in parallel. So I am talking about the resistance between 2 phases. If you're interested in one phase, just one winding package, which consists of 4 teeth, then it's just 1.5 times that, because in series you've got 3 times, parallel to 1.5 times, you end up with that value overall. So according to the web page, that motor over here has a resistance of roundabout almost exactly 10 milliohms. Which also fits to my measurements. With a load current of 100 amps, I ended up with 110 milliohms, so including those cables, which are American wire gauge 4, which is 21 square millimeters. That fits nicely. 10 milliohms. All right, accepted. According to their webpage, it has a cross-sectional area of, how much was it? 8.5 square millimeters. All right, that's it. And as far as I was able to analyze it, it's composed of probably 17 wires with a cross-sectional area of 1.5 square millimeters each. And those 1.5 square, half a square millimeter is based on a wire with a circular shape, of course, and a diameter of 0.8 millimeters. So that one has half a square millimeter and 17 times 8.5 square millimeters. That's good. Furthermore, I measured the inductance, which was around about 174 microhenry. Of course, naked without rotor, because the rotor affects the measurement depending on the position of the magnets, the reluctance, and so on. So that is measured without rotor. 174 microhenries, also face to face, and third one left open. With that value, we can calculate the electrical time constant, which is that one, and over here we've got around about 17 milliseconds, which is okay. It's not too low. If it gets too low, below 10 milliseconds, it's a little bit more difficult to control the machines with the power electronics and the switching frequency, which is usually something about 20 kilohertz. So 17 milliseconds. All right, good. So I decided to have 8 turns. So let's assume that this one, the original one, is not the one with the 9 turns, but with 8 turns. All right. So according to the web page, it should run with 36 kV. According to the web page, this one should have an ohmic resistance of around about 8 milliohms and a cross-sectional area of 9.5 square millimeters. So either they've got 19 wires in parallel or decided for a slightly bigger cross-section. I don't know. In activity, I don't know, but we can easily calculate it because the inductivity is proportional to the amount of turns squared. So in our case, it's the 174 microhenry times 8 squared divided by 9 squared, which is then something like 130 something microhenry. Good. Leading to an electrical time constant of different inductance, different resistance, but around about, again, 17 milliseconds. Less inductance, less resistance, same electrical time constant. All right, good, so far. Now, coming to those ones, those self-made machines with a different cross-sectional area of the copper wires, a rectangular one. So it has also 8 turns. So also as the ideal one over here. Should run with 36 kV. And I already successfully made the first one running, and it turned out that it has a kV of just 33 kV, which fits nicely to around about 10% missing. So that might be because the magnets internally are a little stronger, leading to a higher machine constancy phi, which reduces the no-load speed but increases the torque output, which is perfectly fine for me. At a load current of 100 amps, I measured the ohmic resistance, which was close to 5 milliohms, a little less. Good. So that's much less than the 8 milliohms. That's down to 60%. And 60% is directly reflected in the ohmic losses later on. So if there's current flow, the losses are R times I squared. And with 60% ohmic resistance, you've got just 60% of the losses. Nice. The cross-sectional area over here is 16 square millimeters. Sure, the reduction in ohmic resistance has to come from somewhere. In that case, it's increase in copper, amount of copper. And more precisely talking, it's 10 times 1.6 square millimeters, because over here it's made of rectangular copper with 2 millimeters by 0.8 millimeters, those 1.6 square millimeters. Next step was to measure the inductance. And it was not the 134 microhenries, it was just 125 microhenries, which is a little less. That surprised me a little bit because I expected a result a little closer to that one. Still acceptable, don't get me wrong, but the inductivity is made of amount of turns, iron core, and not about the type and cross-section of copper or material. So I don't know, but that, as I said, it's still okay. Leading to an electrical time constant of, in that case, little less inductivity, but much less resistance, leads to 23 milliseconds. So a little bit more electrical time constants, which slows down the change in current. You know, that's what it is about, which is good for controlling it. So 23 milliseconds is a value perfectly for such a machine. Good. What else can we consider? We can talk about skin effect. Sometimes skin effect pops up. What is skin effect? Skin effect means that for non-DC currents or AC currents with a certain frequency, the current distribution is not equal over the cross-section area of the wire. It is just under the surface, under the skin. And the formula for that one is root of 2 times rho specific resistance divided by omega, which contains the frequency, and permeability, like this one. Okay, and if we calculate the skin depth for maximum rotational speed, which is around about 350 Hertz, we end up with a skin depth of 3.6 millimeters for copper. So that's nothing we have to think about. But, warning, we've got a different frequency in our machines, which is 20 kilohertz, the PWM frequency, the switching frequency of our motor controllers, and then we end up with round about 0.5 millimeter skin depth. That's still something, nothing to worry about in our machines, as long as we have copper wires with 0.8 millimeters diameter or thickness, like in that machine. But nevertheless, if it plays a role, we can ask for the skin, the circumference, and for the original motor, we've got 17 times circumference, 0.8 millimeters times pi. We end up with a total circumference of 42 millimeters. And for that machine over here, we've got 10 times around that one, 5.6 millimeters, which is then 56 millimeters. So also more skin, more surface. So if skin effect plays a role, that's also an improvement. Not as much as for the ohmic resistance and the cross-section area, the amount of copper inside of the machine, but still an improvement. What else do we have? I think that's all. I already talked about the outer cables. That is 21 square millimeters. I increased to 35 square millimeters. So also less losses in the cables outside of the machine. Overall, that's lots of theory. The truth is waiting inside of the vehicle as soon as it's moving. And of course, everything I did affects just the losses due to current flow. It's not about hysteresis or magnetization losses, eddy current losses, ventilation losses, but nevertheless, at a current of 200 amps or even more, you can easily have 300, 400 amps through those machines, phase current, that should lead to significantly less losses. But yeah, time will tell. Maybe in 1 or 2 weeks, the machines will be live in the vehicle. So next step is to swap the rotor of the second motor around that one. That's also not that easy because of the strong magnets and the bearings and so on and so on. But anyways, at least once it worked, as you can see. Good, coming to an end. What's missing? One important thing. I'd like to thank the guys from Revolt 1,000 times. They really helped me a lot, and as I said once before, this is kind of open source project. They shared all the information, all the material I'm asking for whenever I've got a question, either simple, stupid, or difficult. They are willing to help me, and making that perfectly clear, even though it seems like a huge improvement, producing those winding packages with a rectangular cross-section is nothing you can do in a mass production, or at least I couldn't imagine it. So those machines, the original ones, are already on a very high level, very high efficiency, and they worked perfectly fine in the Twizy. So honestly, there was not a real reason for that project. It was just, once again, as usual in my life, curiosity, and yes, I can improve things which are already close to perfect. All right, guys, so now enough of talking. I hope you understood everything. I hope it was free of any mistakes, errors, and if you find something which is apparently wrong or missing, then just feel free to tell me. All right, see you next time. Goodbye.